Okay, I think it's start. Good evening, all. Hope you're all
Today,
colleagues. Yeah. Have you guys covered temperature stress to begin with? I'm just gonna go over some theories at fine, and then we can begin. Is that okay? Just to be sure.
okay, so
Yeah. Um, the aim is to complete 2 questions in module 3, and then also just go over the test quickly. Obviously, not all the problems or not all the questions were bad for students, but I mean, I know the one I want to go over the most, which is very important for the next test even. So yeah, let's just open this one up and then let's get cracking. Okay, so module 3 is about temperature stresses. I assume that everyone has obviously watched the recording and went over what they need to go over. So I just want to come to the salient or the important sections regarding temperature stress. And I'll begin immediately. Um, so much to cover with all these things here, but anyway, yeah. So I'm not going to talk about. I think I mentioned in the recording regarding how it works. Different materials have different expansions. I want to just uh come to the part of where I need to bring. Okay, so it's so the just like the previous section of compound boards, we have series in parallel. We have a similar setup here with temperature stresses, right? We mustn't confuse the two. There are two different loading conditions. But that being said, let's look at temperature. And of course, please um, ask me questions as I move along. So the series arrangement, right? You'll notice it starts over here, 2 boards in series. And the idea is that um, the main the main setup with this is they will put 2 bars in series, which is like this. They clamp both ends. Then what happens is they apply what's the word I'm looking for? A temperature increase, right? So obviously, no, as we increase temperature, we'll get a extension, and as we decrease temperature, we'll get a contraction or it's reducing length. But in this case, there's an increase in temperature, and then something happens. So what what happens is I don't think I can draw here on this one. Okay, so let me just quickly copy this to the whiteboard rather so I can actually explain to you what happens. And it seems difficult, but if you get the gist of it, it's essentially 2 different types of question. In fact, 3, if you're considering the bolt setup as well. And if you practice those series in parallel, you basically ready. And understanding is fairly understandable, in my opinion. It's not too difficult to comprehend. Let me just share the whiteboard again. So the standard setup is you have 2 boards in series like this. I'm not sure practically where this is the case. There are various effects of temperature effects in the practical sense, but in this case, just here. So what happens is we apply a heat, right, to the system. Okay, so we heat it up. There's a change in delta T. And when this happens, right, you'll notice that this bar, and like this, it wants to obviously extend, right? Okay, is that fine to everyone? You can see I'm putting the arrows to the, two arrows going the other way. I see that it's extending, right? I hope you guys can make out of what I'm saying. So as these bars extend, right, because it's fixed, what's actually happening at the ends here, you'll notice that it gets compressed like that. That's a very important concept. If you look at the arrows from here at that junction to that junction, you'll notice that material 1 is being compressed and material 2 is being compressed. And that tells you the sense of what's happening here. But what is the other factor here when you're looking at the equations, right? And again, I'm assuming we all went over this, so just bear with me. So that is, I'm just speaking in terms of in that way. I'm not explaining it from scratch. I believe I did mention in the videos that how it works. Um, that force, right, which I'm talking about as it's extending, the supports are supplying a force. What is key to note, the forces are equal in magnitude, right? However, the change in length you have to add. The change in length in question are, the first change in length is the increase, right, of the thermal side. So the material 1 is going to extend, material 2 is going to extend. So we call this the thermal side. And then we have the mechanical side. And the mechanical side, what I mean by that is is this actually added? Yeah, I feel a bit uncomfortable, but it's fine. This is caused by the holes over here. You know, the how do I say, as the bar's extending, the holes are compressing the bar. And that compression is essentially the FLA over E. And as you take out common factors on the one side of the force F, because F is the same, you take a change in T, you end up with this. So this over here is basically the series standard formula for the temperature thing. And don't confuse the previous section series with this one. It works differently. It seems the same, but it's differently. So I hope that's clear to you. So I want us to apply these principles, and what is key is, as I solve, I want you to ask questions. Is it fine, colleagues? You guys got me?
Yes.
Yeah. Okay. I don't know you there. Simpi, are you there? So if you don't understand, just say, sir, what is this again? I'm like, let's unpack it. So let's go straight. So this one, it's in the Google Classroom. It's a question I didn't solve in the recording, so I obviously decided to choose this one. And let's read. So we have a copper and a brass bars are placed end to end in a series connection. Long story short, if you want to look how it looks like, it looks exactly like this. So maybe I can just steal the sketch. Let me just steal something else. You can see it. Print screen. Okay. And then put it over here. Right. Bring it forward here. Let me sketch it rather here. It's going to be just, so we have, again, we have two bars. It's always going to be typically the same arrangement, but there is some deviations. So these are two bars in series. They'll state a particular keyword now. It says it's fixed between 2 points, then no change in length can occur. So that means it's rigidly in place. There's no gap in the middle here, which can happen sometimes. Use the data below to answer the questions. The system is heated up to 60 degrees, right? Okay. So we have a change of 60 degrees, right? So normally you must be careful in the questions. They might give you an initial temperature and then it's heated to a certain temperature. Then you must find the difference. Is that clear to everyone?
Yes.
You guys get that? So sometimes I'll say the initial temperature was 20 degrees and it's heated to 60. That means you must say 60 minus 20. But if they just say, like it's subjected to a temperature difference or it's heated up to 60, it just means you have to use 60. So just be careful with the wording sometimes. Yeah. So then obviously we have to classify our materials. So we can say the first one is the copper bar, right? And the second one is the brass bar. And obviously it comes with certain lengths. Must I actually sketch this one? This guy is 200 mil. And this guy over here is 140 mil. Right, so as we heat this bar, like I said to you, what's going to happen is, obviously, I don't know if you're aware of these principles. This guy is going to want to extend this way and you want to extend this way. Likewise, with that one, the brass and that one. However, because it's fixed in place, right? The wall will resist. And by the virtue of it being fixed on that end, the bars will be compressed. This bar will be compressed. The same principle applies here. It wants to go it wants to go that way, but there's a force acting that way and a force acting that way. So both these materials will be compressed. That is the key here. The nature of the stress. If if the temperature was dropping and not heated, the system will act differently. The bars will actually will be subjected to a tensile stress instead of a compressive one. So that's a very important thing to note. Okay. Now, the first question states the stress induced in each material. Stock standard question. Okay. Now, if you look at the formulas, when you compute the stress, and unfortunately, we don't have anything directly related to stress. So then what we need to do, we have to come to this formula over here, right? The change in length of 1 plus a change. So it's the thermal side. I'll write it for you here, explaining the thermal expansion, right, or elongation, whatever you want to call it, is equal to the mechanical elongation. Again, this is by the virtue of the whole compression material. And you'll see it when I do 2.2. So I'll just say mechanical elongation, just to make it different. So we know that on the thermal side, the change in length 1, the thermal expansion of that must increase, that must be there. And that's going to be equal to the total, this is why I'm comfortable in terms of the signs, but it'll be equal to the mechanical side, so the Fleet of each one, right? FLEA, the elongation, right? Remember, this is just X. I don't know if you guys remember that, no? You guys remember that from the previous section? So that's like that. Okay, so once that is done, like I said to you, we need to find the force. And the reason why we're finding the force, because the same force is essentially compressing this thing. And therefore, that's, as you see, F1 is equal to F2. And they state there, because the 2 bars in equilibrium, the force acting on each is the same. So all I want you to do now is use the actual formula for contraction. So obviously didn't mention that, but the formula for contraction, assuming you went over the lecture, is your coefficient of expansion, that L, and then delta T. So this will give us an increase in length. So I'll write out the first one, and I want you to do the second one. So L1, let's just call it copper, or let me just say copper here, and let's just call this one brass. And this will be copper, and that'll be brass. So the first change in length due to the thermal expansion, it's going to be your coefficient of expansion of 18, right? Times 10 to the negative 6. Okay. Times by the length of 0.2. And we times that by the change in temperature of 60. Is that clear to everyone? So that's when you heat up the copper, it will expand by that much. Is that fine for everyone? Okay, I don't know what that is. So can you please tell me what is the thermal expansion for the brass bar now? Give me the words. Give me the numbers, sorry. All on the screen. What is the numbers? What is my thermal expansion? Hosi, Simpiwe, Aiden.
Sir,
Yes.
it's gonna be the 22,
100%. Thank you, Chief.
the 22 times 10 to the power of negative 6,
That's correct.
multiplied by the 60 degrees Celsius,
Yes. And the length?
and the length is 0.14.
Perfect. So that means you've got that side. Obviously, this is the one side of the equation. That's fine. Thank you, Aiden. And on the other side, you obviously have to, we take out the force as a common factor over here. And we need to now do the LEA of the copper and L divided by EA of the brass. So the length, I'll do the first one for copper, that is 0.2. I'm pulling this down, you can see over here, we've got copper's 100. Okay, I should have known that. Then our area is 380, but in meters squared, that should be 380 times 10 to the negative 6. Let's delete this here on the side quickly. Okay. And then we plus 0.14. And then we have our brass, that's going to be 80. Okay. And then each respective area is given as 500 millimeters squared. Okay. And that's times 10 to the power negative 6 over there. Is that fine? So all you have to do is solve for this F. Can you guys do that for me? Should be easy, right? So that's this divided by all of that. And we should get an F value. So maybe some people can do that for us. So once you're done, you can just say the answer to me.
Okay.
Sure. And guys, please do not show ask questions. I'm here for that, man. You know, but you must put in the work. Oh. Just check if I have these answers somewhere. Sure. No, man. Okay. Yeah, I think it's there somewhere. Just let me know when you get the force. Yes.
Yes.
Yes,
Okay.
Impile.
Okay. Okay, this will be 8 comma. We're calculating the one on the right.
Okay, that's fine. You can do that. Yes, yes, yes.
This way on the right will be 8,763 times 10 to the power 9.
Okay. Right, that's fine. 763 to the power 9, and then on the left.
So there's a, I think that's
On the left.
to the power
Yes.
of negative 9.
Negative 9. Okay,
Yeah, negative is negative 9.
that's fine. No problems. But I can assure you, if you practice those 4 questions I put up on the Google Classroom, you should be sorted. However, there is another question regarding the bolt, which I'd like to do. It's another key, a very important one, regarding temperature stresses. And what's on the left?
1,848 times 10 to the power minus 4.
1,848 times 10 to the power 10 to the power negative 4. Obviously, now we just have to
Negative
solve for
4.
F. Negative 4. Thank you. I know my 9s and 4 look the same, but I mean, I think that's a 4. And you just have to solve for F now, which obviously will be the 1 divided by the other one. Okay, colleagues, what is my F?
Would be 21,077 kilonewtons.
Let me check. I don't think that's the right answer,
Are you
colleagues.
sure?
You must just have a look. Yeah, it's not
Unless
the
I'm
right
correct.
one.
Okay.
Yeah, I have the answers in front of me. That is why I'm saying that. Just check your right and your left side, no? If it's correct. Just verify.
So
Yes.
I think that left answer should have been 4,008 times 10
Okay.
to the power of -4.
4,008. Okay, and then what is my F's answer? My force. What's the
Then it's gonna be
that is correct.
45,738
Yeah,
kilonewtons.
yeah, that's correct. 45.73738, right?
Yes,
7
sir.
or 8, was it? Okay, 8
738.
kilonewtons. That is correct. Colleagues, if we all get that, just check. I'll just give it a minute or so. Okay. Push in if you can see that's true. And remember, so the main part of the question is to find the stress. That's quite easy. We come to the copper, right? And it's just going to be force over area, right? Of copper, and we're going to find the brass. In this case, it's force over area. Okay, so you guys can quickly do that. So the same force, which was in the force was applied by the supports, and all you're going to have to basically do is take that same force. That force is 45.738 times 10 to the power 3, and you divide it by the area of the copper, which was 380. When you get an answer, that's -6. And then over here, you take the same force again, 738 times 10 to the power 3, and then divide that by 500 times 10 to the power 6. And obviously, you're going to get your two stresses. So I'll just wait on you guys to give me two stresses, and then, yeah, we can move on. That'll be 2.1. Right, college, what do we get for the stresses? What do we get? Aiden, Boosie, and Simpiwe, what do we get?
Stress for copper is 120,363
That's correct.
megapascal.
And to ask you, Aiden, is that a tensor or compressor stress?
That is going to be compressive.
That is correct, yeah, right? So it's being compressed by the walls. On the other side, for brass,
91,476.
91,476. I believe this is correct. And it's
Megapascal.
also being compressed, yeah, megapascals. And it's also being compressed as well.
Yes,
That's
sir.
2.1. Yeah, that's correct. Very important question, comes a lot up in the past papers. Yeah, I hope, is there any questions before I proceed to 2.2, colleagues? I believe Aiden is falling. I'm not sure if Boosie and Simpiwe, Mr. Faku is there. And that's all 14 marks, which is a lot. Yeah.
Sorry, sir, can I ask a question?
Yes.
I'm still struggling there by thermal expansion. I
Okay.
don't get it.
You don't get this one.
Yes, the side of thermal expansion.
Okay, that's fine. Let me have a look. I'm going to share my calculator so you can see. As long as you understand it's expanding, that's the first point. And then obviously we have to add the two expansions together because they're in series. So let me just do the calculation and see what you guys, maybe you're trusting my handwriting. It could be a problem. Let me see. So you can see my calculator, right?
Yes, sir.
Perfect. So we're doing that. That's times 0.2 times 60. Is that fine? Plus
Yes.
22 negative 6. That's going to be times 0.14. I wonder if you saw that times 60. You see there?
Yes.
That's it. That's the answer. So what do you think you're missing? You're just adding this plus adding that over there.
I think my mistake was saying 60 times all of that.
Oh, I see. Again, okay. So it's like that plus that there. That one change in length plus other one. Are you fine with this?
I said 60 and then I put brackets. And
Oh,
then
but that's also fine. You can do that. So 60, right? Brackets now. Can you see? 18 times what? 0.2 plus. That's you're talking about this, right?
yes.
Shouldn't be a problem. Times 0.14, right? Close the bracket.
Oh, I don't know where the 0.14 came from.
It's the length. Remember, the formula is the coefficient of linear expansion times length times change in temperature. If you've obviously went through the section, you're off. Yeah.
All right, thank you, sir.
I see. Okay, so let me just reshare now, and then we can proceed. Okay, over here. So that formula, Boosie, like I said, if you, assuming you guys went over the recording, the formula for thermal expansion, right, looks like this. You see it there? It's coming now. Do you see it? That one.
Yes, sir.
You see it? That one there. Length, coefficient of expansion alpha times change in T. Can you see 3 variables?
Yes.
Okay. So now the next part of the question, they're asking the distance the connection has shifted owing to the change in temperature. So what that looks like is essentially this part here. So we have two bars, they're both at a certain length. And now if you look at this image over here, obviously there's going to be a shift due to the increases in length and obviously the compression, which I mentioned. So we're gonna have, so we were like this, and after the 60 degrees, we end up with a movement like that. Is that fine for everyone? Can we all imagine that? So before we had this, after it's been heated, it shifts like that. Is that fine?
Yes, sir.
Perfect. So what we want to know, how much from a particular point, right? Let's say from here to there, or from there, from here to here, how much is actually shifted. So that's what we actually be working on now. And the way we do it is quite simple. We come over here. So again, the distance, the connection has shifted owing to the change in temperature. So that's what we're doing. So to do that, we just have to consider either side. So let's say we're going to consider copper. Excuse me. Let's just consider copper. So we're starting from the copper side. Okay, right. So the copper was, I believe, on the right in our case, which is that one, right? And the total change in length, right, or the amount it's shifted is quite simple. So I'll just say, what do I call this? X. I just want to see a reasonable thing to call it. Yeah, you can say final length, maybe X final is going to be the following. It's going to be a thermal expansion of the copper, right? Which is obviously the one that you know. But now you're going to have to, we're finding the final length, but we're finding the distance. The distance is just shifted. Okay, so we're not finding in the case of. Let me show you what I'm talking about. So what they're looking for is this shift from from here. Can't go straight. So how much from here to here it has moved. Sometimes I ask for the final length, and the final length will obviously be this piece over here plus that piece over there. But we're just now finding this piece over here. And to do that, it will basically be the expansion due to the temperature. Then all we must do is then subtract the mechanical part. And the reason why I'm subtracting is because it got compressed by the virtue of being supported on the one side and being fixed on the other side. So that would be F, L, E, A, and then copper. So I'll say that again. The amount it shifted was we got an increase in length due to the thermal expansion, but because it's fixed on one side against a wall and it's fixed and it was joined, it got compressed, and so therefore we must subtract. So you can actually do the same thing if you consider the brass. You'll notice that it's the same. It'll be very close in terms of the shifting will be exactly the same dimension. It cannot be different, obviously, if you think about it. They must have shifted position by the same magnitude. So all we have to do is just plug and play the stuff that we have. In this case, it's 18 for the copper. Okay. And I want to try for both. You times the length. The length in this case is 0.2. Okay. Times the 60. And now we must minus the compression. And that is why I was unsure that sign made me feel a bit uncomfortable. 45 point, what is it, force now? 738 times 10 to the power 3. The length for that was 0.2. And then we're dividing by 100 times 10 to the power 9. And you times that by 380 times 10 to the power negative 6, which is the area. So you can just quickly work out that distance it shifted, right? It's not the total distance of the ball or the final length of the ball. No problem. I hope you're following. So you can just quickly work out that changing. Yeah. Okay, just get that changing of the position, please. So what is my change, or how much has it shifted by? Should be a very small amount. So what do we get, colleagues? Aidan, Busi, Simpiwe.
My answer is 24,715.
That's correct. Yeah.
Negative
24,7.
716 times 10
Yes,
power -6.
perfect. That's correct. And that's meters, no? So
Yes.
now I'm going to prove to you it is shifted the same on the, consider the brass. So you must do the same now for the brass. Consider brass and that shift, right? Not the final length, how much it's going to be the changing thermal expansion of the brass minus FLEA of the brass. Okay, so again, it extends thermally and gets compressed mechanically by the ends. So the brass was 22, I think. Right, times 10 to the power -6. Each length was 0.14, I believe. And you times that by 60, you minus the 45.738 times 10 to the power 3 by each respective length of 0.114. And we divide all of that by EA, and the E for the brass is going to be, what is it again? 18, 18, huh? Yeah. 80 times 10 to the power 9 times each respective area, which I believe is 500. So Push, you can just confirm this. And what we're looking for is that you notice that this answer and this answer will be exactly the same, or very close to each other.
My answer is 24,717 times
Yeah.
10 power negative 6.
So can you see, Bushi, it's the same basically. It doesn't matter which side you consider, as long as you respect the material properties. Can you see that, guys? Aiden and Simpiwe? Are you guys
Yes, sir.
still there? But can
Yes,
you see
Yes,
it's the same? Yeah. Yeah. Is there any questions now? So we can consolidate any understanding you're not sure of. Let's just take 2 minutes to just unpack that. Please tell me if there's anything which is unclear there. Done? I'll be fine. Okay, so what I'm going to do now, I'm going to do a parallel setup. And it's going to be similar to, yeah, a particular question that you've done. Okay, so I think I wanted to do the other one, but I think time is catching up with us. And so therefore, I believe this would be the better option to just quickly do this one instead. But let me just get let me just convert it to PDF quickly. So this is question 3 in your test. Yeah, so I thought I'll do this and then I'll integrate that with the new work. Yeah, so just give me a second. Okay, just give me a second. I just want to convert it quickly. All right, so we're going to go into the parallel aspect of this particular one. So just check now. I'm going to send you an image. I can find it now. For some reason I'm not seeing it here. Quite strange. Okay. Let me see. I can't see it here. So yeah, it's just converting quickly, and then we're gonna go over the. So while it's converting, I'll just go over the parallel. So I'll share. And students, I'd also like if you guys can send questions beforehand, if you do have questions, and I can solve them for you. Okay, so just can we see the text? Colleagues, can we see the text over here? The text or the book?
yes.
Okay, cool. So now with the parallel setup, right? It's essentially 2 bars, right? Typically one inside the other one. Now I just want to open this rather because I think this textbook doesn't have what I'm looking for. Just want to show it to you. See. Image come now. I'm gonna, yeah, okay, this is what I'm looking for. So yeah, the key thing is here is you have 2 materials in parallel. I'll show you what it looks like in another textbook. It gets heated, it will thermally expand. However, what's important in this case is that the expansion will be a lot different in that the one material will be a bit longer, right? It'll increase by a certain length. and another one will increase by a certain length. So if you look at change in length 1, it increased by that much. That's the thermal side. And the second one is increased by that piece over here. However, this is typically fixed on both ends. I don't see a good image here. That's why I want to show you the other one. But if it's fixed on both ends, like in this case, you'll notice that material 1, right, because it's fixed, it will actually be compressed due to the wall. However, material 2, in this case, will experience a, okay, yeah, this is what I'm looking for. Yeah. It will experience a tensile force. And once again, they say that the two bars in equilibrium, and therefore the force is acting the same. So like I said, with parallel temperature, right, it's not force 1 plus force 2 equals, you know what I mean? The total force equal to the sum of the forces. And they will say here that the tensile force in that material 1 with a higher coefficient of expansion puts on material 2 is equal to the compressive force that material 2 puts on material 1. But what's key, and you'll notice that when we do the stresses, you'll see what I'm talking about. And then now our conditions are slightly different, where we have the change in length of 1 will be positive as it increased, but in this time around that the change in length is subtracted, not added as the previous one. What they also do, they take out the length as a common factor, right, by each term, and therefore you're left with this formula over here. So this formula would be the one for parallel, just over here. That's what's key. Given that you put the material with a higher coefficient of linear expansion over here, that's the key. But to illustrate this a bit better, I want to show you what it looks like from this. And if you want this particular book, and then you can obviously, I'll share it with you. So this is what I'm talking about. So you have one material inside the other one. If you freely expand it, like I said to you, assuming that there's no fixed end, again, in this case it's different, where the one on the inside is growing faster than the other one due to its higher coefficient of expansion. And you put it fixedly, you'll notice that material 1, like if you draw a line over here, you can see that this one will be compressed over here, and this material 2 on the outer ends will be in tensile. So that's a very important case. And they state here, like, compressive force in the first one is essentially equal to tensile force in the second, which is over there, which is the converse of what I talked about. So now I think what I will do is we just do a question. And yeah, I hope you're gonna get through it. So you can treat this as a recap on the test as well, because it forms part of question 3 in the test. So let me just open the whiteboard. And you can see. Okay, and I'm gonna paste it now. If I share, just confirm you can see the whiteboard for me. Did you guys see it? You guys see the whiteboard?
Yes, sir.
Yes, sir.
Okay, cool. Let me close this off. And then put it up like this. So you guys remember this question? They give you a headache. You guys remember this one?
Yes.
Sure, it came from the test, right? So how these questions for parallel typically works. There's 2 parts to it, right? The first part is the mechanical part that you know, the normal module 2 type stuff, okay? And then what happens is they integrate a second part of the question, which looks like this. Okay. And the second part of the question is now, so what they do in the first part of the question, they'll first say, okay, we have two bars, it's loaded by 65 kilonewtons, right? We have to find the stresses. Subsequently, we then now raise the temperature to, we raise the temperature to 37 degrees, and there's temperature stresses induced in the material. However, we need to now find the resultant stress between the first section in mind and the second section in mind. And this is module 2 over here. I'm sorry, module 3. Is it clear to everyone? So the first part is always to do module 2 first or module 3 first, and then we have to kind of integrate the two. I hope you guys are with me. So let's quickly do this one first. I don't know if you've picked the pattern up anyway. So yeah, just remind me, what arrangement do we have for this one? What arrangement do you see in front of you? You've got a bar fixed on two ends and it's loaded there of 65 kilonewtons. What arrangement is this?
Parallel, sir.
Exactly. Can you remind me the formulas which accompanies parallel again? The force and extension one. Before I read the question. You're checking your book, Pussy.
I think
So if
this
you
one,
remember, it's force total equals force 1 plus force 2, right? So that 65 kilonewtons will be distributed between those two things. In this case, we're going to say force of steel and force of copper. Is that fine? Are you happy with that?
Yes, yes, sir.
Perfect. And we know the total change in length, it will be equal to the length in the length in steel and the length in change of length in copper. And the reason why they're equal is because they have the same length. So they'll both be elongated or compressed because they're the same length. Is that fine to everyone?
Yes, sir.
Perfect. So let's unpack this question. So what the question states, we have a compound bar. As you can see, it's part of a machine frame. We have two parallel bars, a steel bar and a copper bar, and they're both undergoing a compressive load of 65 kilonewtons. It's stated they are both 127 meters long, so they're equal in length. The steel bar is 15 millimeters in diameter, and the copper is 20. Obviously, they both have their own respective Young's modulus. And the first question is, what is the stress in the material when it's loaded by 65 kilonewtons? Okay. So remember, the first part of this question is, because we know the change in lengths are the same, we need to find two ratios between the two. So remember, we have FLE, remember? FLEA and FLEA, okay, FLE. So this one is for the steel, this one is for the copper. But remember that the lengths are the same, so we just have F over EA equals of steel, and we have F over EA of the copper. And what we're looking for is a ratio between the two so that we can resubstitute back into this over here. So to do that, we're going to say F over steel is 215, right? Times 10 to the power 9. Its area is going to be the following. Because it's a cylindrical section, it's pi over 4 times what again? What is it called? It's 15 more. 0.015 squared. That must be then equal to F on the copper side Okay. And that's going to be 145 times 10 to the power 9. And each area in this case is 20 more. Okay. So, oh, obviously it's pi over 4. So what I want you guys to do is get for me the ratio between the steel, the force of the steel and the copper. Can you guys do that for me, please? Thanks. You guys got that, eh? What you must find. Aiden, Pussies, Imperial. I'm just waiting on the ratio.
I got 834,0552 times 10 to the power negative 3.
Okay, so what I'm looking for Pussy is the ratio between the two. You understand what I'm saying to you? So you're going to times this part on top of there or this part on top of there. You got me? So what I'm saying is you're going to find a ratio between the two. So if I do it like this, it's going to be 215 times 10 to the power 9 times pi over 4 times 0.015 squared, right? And then you must divide that by, obviously, this over here, 145 times 10 to the power 9 times pi over 4 times 0.02 squared. Are you with me? Aiden, what did you get?
What I did, sir.
Huh? You
That's
do
what I-
that? Okay,
Yes.
so what is this idea? Is it Fs equals what? This is what I'm asking.
Fs is equal to 834,052 times 10 to the power negative 3 FC.
Okay, so say it again.
834,052 times 10 to the power
8.34, no?
834,052
Oh, comma 052. Okay. That's fine. I get you now. Perfect.
times 10 to the power negative 3.
Yeah. 834 point that times 10 to the power negative 3. Okay. That's fine. 0.834. That's fine. So once we have that, we must now resubstitute, right? This into that formula. So our total load, if you recall there, was 65 kilonewtons. Okay, as you should have remembered in the first. Let me know we have Fs plus Fc. However, we only want one unknown here, so we have to substitute this guy over there. Am I right? And then we're gonna have Fc equals 834.025 times 10 to the power negative 3 plus Fc. And now I want you guys to solve for me for Fc. What's my force in the copper? Obviously, you want to get the forces so we can obtain the stresses. And let me know once you've completed that.
I'm not sure about my answers there, but I've got 35,44
That sounds right. Trust yourself, trust yourself.
kilonewtons.
Yeah, 35. So say 34 what?
35,
35.
44.
Perfect. And obviously to find the ratio of steel, you must just times it by that, am I right? Or you can say 65 minus that, or you can say this times that over there. So what is my steel? So maybe I can just say F steel is 35.44 kilonewton times the 834.025. So how much is the steel carrying? And we're basically solving what was in the, what is this thing called again? In the the question paper.
I got 29,55.
Yeah, I think that's correct. Let me just write that 29,55. So that should be 29.55 kilonewton. And once that is done, obviously all we must do is find the stresses, right? So stress of steel is Fs of steel divided by the area of steel. And then the copper is going to be Fc over AC. And yeah, so Boots, I think you worked out the areas already, so can you just find the stresses for us as well? I don't know where are the other colleagues here. So each respective one. Simpiwe and Aiden, are you guys still there?
Yes, sir.
Okay, so can you just get the force of steel and the force of what is it called again? And the
Say again, sir.
sorry,
Say again.
we find the stresses now. We found the forces.
Oh, the
Yeah.
stress of steel is gonna
Yes.
be 167.27 megapascal.
Okay, that's cool. Oh, you've done this before, no? So you know it. And then the stress of the
Copper.
what is this? The copper is a 112.
Yeah.
Am I right? Yeah.
Yes, sir.
Okay. Perfect. So what are the sensors of these steels? Are they being compressed or the tensile?
Um,
Question is there.
It's not supposed to be compressed.
100% true. Thank you. They're both compressed. Okay. So yeah, we technically did the first part of the question. Then I'll just quickly show you the final length under the compound under given conditions. So most students made a mistake. So the final length, our final will be equal to the length given minus, right, the change in length due to whatever. So the length you can choose. You can either do it or the steel or copper. I'll choose steel. But most students did, they added a plus. The reason why this is negative because it's being compressed. Is it clear to everyone? Is it not so when you compress something that the length becomes smaller? Is that correct? Exactly. So now let's quickly do that. So the length was given as 0.127. And then all we have to do is do our Flee formula for the steel, which is essentially that part over there, all right? So we know the force is given as, for steel was given as 29, thanks to Busi, 0.55 kilonewton. We must times it by the length again, 0.127. We must then divide by the modulus of elasticity, which is 215, and times by that area over there. That's 215 times 10 to the power 9 times pi over 4 times 0.015 squared. And that will give you the final length. So be conscious, if it was a tensile force, that would have been a plus. But because it's being compressed, obviously the length must decrease. So can we get that final length there quickly? What is my final length, colleagues?
I got 0.127 meters.
No, man, it must decrease. Give me all the other units. Call me 0.127. Where's all the other decimals? Remember, I know it's small. But it's like, it could be 127. But I mean, like, it shouldn't be 127, man. It must be less. Like 126 something 9. You know what I mean?
Oh, it's 126.9 times 10
Yeah.
negative
Yeah,
7.
that's correct. Yeah. Something like that. You understand? It's a small decrease. Yeah.
I just rounded to the 3
I know. Yeah. I know what you did. So is that fine, everyone?
Sorry, sir.
Yes, in period.
I don't know if I say properly, 29.55.
Yes.
Is it 10 to the power 3? It's not supposed to be 10 to the power 6.
No, Chief. Remember, this is a force we're dealing with.
This is the force. Okay,
Yeah,
okay,
yeah.
no, I check the force and not the
Yeah,
steel.
okay.
Not the, okay, I see.
Okay. All right. Is that fine? So, colleagues, tell me, do you have a session scheduled for tomorrow? Who's here, Aiden Simpiri? Sorry?
No, I don't have.
I don't have.
Okay.
I also don't have.
So I'm thinking, are you guys available tomorrow at 6?
I
I
am.
will
So
be
you-
available, sir.
Okay. So what I
Yes,
want us
yes.
to do tomorrow, I want us to stop now here. Then I want us to continue with that piece over here. Is it fine? So I'll put the recording up tomorrow morning. Then if you have time to practice, but I'd like to continue the last part tomorrow. Is that okay to everyone?
It's okay for me, sir.
Thank you, Busi.
Yes, it's okay.
Okay. Okay. Then, yeah, then I wanted to give you guys homework, but what I do recommend, if you can solve it by yourself, it'll be great. And then, yeah, you can maybe take a picture now and try to solve the temperature. Then I'll obviously continue tomorrow. And the others must just catch up. Is that fine? Just let me know when you got the picture, and then yeah, we can close today. Then tomorrow I'll just come to this piece and then we're done.
Thank you, sir.
Okay, thank you very much, guys. And guys, the prescription for the subject is the following: 1.5 hours per day, 6 days a week. You need to be, that's the energy you must give the subject. It's demanding. Yeah, but you can definitely do it. And if you have a question, you can post on the group and I will answer. But you must put the energy in. Okay, guys, I'll see you tomorrow. Then we'll complete this last section. And then yeah. And make sure you check the Google Classroom. If you all my other videos are on that channel if you want to find different ones. Some of them are the same, I repeat, but you can go over them as much as possible. Okay? So I'll see you tomorrow. Thank you very much.
Thank you, sir.
Cheers. Thanks, Aiden. See you guys.